Hello everyone. In the previous lecture, we discussed about the characteristic table, excitation table, circuit diagram, state diagram of the SR flip-flop and the JK flip-flop. In this lecture, we will discuss about our next flip-flops, that is our D flip-flop. D means the delayed flip-flops or the data flip-flops and the T flip-flops. In this lecture, we will also discuss about the one condition that is called the race around condition. This race around condition is the drawback that occurs in JK flip-flop. So we will discuss this race around condition in detail in this lecture. We will also discuss how to convert one flip-flops to other flip-flops. Fine. So now we will start our first topic of this lecture, that is our D flip-flop. So the full form of D flip-flop is sometimes it is also called the delay or data flip-flop. Both these D flip-flops and T flip-flops we can derive from our JK or the SR flip-flops. So first we will study the block diagram of our D flip-flops or the circuit diagram of our D flip-flops. So you all know this is basically the block diagram of JK flip-flops. So JK flip-flops have three inputs, J, K and the clock here, and two output, one is Q, second one is Q bar, right? So now if we connect one NOT gate at this input now, and this input I am denoting, this is the D. Now this is our D flip-flops. Here in the D flip-flops, it is clear that the value of J is equal to the D and the value of K is equal to the D bar. Fine. So here if I am saying always D equal to the 1, then J becomes 1 and K becomes 0. In the other case, when D equal to the 0, then J becomes 0 and K becomes 1. Fine. Now similarly we can derive this D flip-flops from our SR flip-flops. You know SR flip-flops also have the three input, one is S, second one is clock, third one is R, and output is Q and the Q bar here. Now if we connect one other NOT gate at the input, then it becomes the D flip-flops. Here the S is equal to the D and R is equal to the D bar. Fine. Now we will study the truth table of these three flip-flops. In the truth tables, basically here the input is one input is our clock, second input is over this D. So this is our second input and output is Qn plus 1. Next state. Fine. So what happens if clock is 0? If this clock is 0, then similar to the JK flip-flops, if clock is 0 in the JK flip-flops or the SR flip-flops, what will be the output? Output remains in the previous states, and that is called the memory. Fine. So what happens in the next case if clock is 1 here and D is 0 here? If D is 0, then what happens here? J becomes 0 and K becomes 1. What is the output of JK flip-flops or SR flip-flops when input is 0 and the 1? Then in that case output is 0 and we are saying this is our reset state. Fine. What happens in the next case if clock is 1 and D equal to the 1? If here D becomes 1, then here J becomes 1 and K becomes 0. What is the output of this JK flip-flops when input is 1 and 0? Here the output becomes 1 in this case, and this is called the set state. Fine. So we can say here Qn plus 1 is basically equal to what? Qn plus 1 is basically from here. So both Qn plus 1 is equal to the D here. Fine. So this is the Boolean expression for the D flip-flops or the characteristic equation of the D flip-flop. Now we will study about the characteristic table of D flip-flops. So the characteristic table of D flip-flops, we know here the inputs is T and here Qn is our what? Previous states, and Qn plus 1 is our next state here. So what happened here? If D is 0 and we are saying previous state is also 0, what will be the next state according to this truth table? Here the next state is basically similar to the here the next state is basically what? If D is 0, see from here, from this truth table, if D is 0, output always remains 0. Okay, that is independent of the previous states. If D is 0 and previous state I am saying 1, then what will the output in this case? Means Qn plus 1 remains 0, because if D is 0 here, outputs always remains in reset states, means the 0 states. Fine. So this is 0. What happens if D is 1 and the previous state is 0? It always remains in set state. Similarly, D1 and Qn1, it always remains in the set state. So this is the set state. So this is the characteristic table of this D flip-flops. And from this characteristic table also, it is clear that Qn plus 1 is always equal to the D in case of D flip-flops. Now, next is over the excitation table. Next, we will study the excitation table of D flip-flops. You know, the excitation table means the here we will evaluate the inputs from the outputs. So here in the excitation tables, we are taken inputs is Qn plus 1, and here the output is G. Fine. So here what happens? If Qn, there are 4 combinations here, 0 0, 0 1, 1 0 and the 1 1. What happens if both Qn plus 1 is 0 0? We know Qn plus 1 is equal to the D here. So that's why 0 1 0 1. According to this characteristic equation, Qn plus 1 is equal to the D always. So this is the excitation table of the D flip-flops. Next is the state diagram. How to find the state diagram from this excitation table? So you already know there are 2 states. One is 0, second one is the 1. Fine. So from the excitation table, if the present state is 0, fine, and the next state is 0. In which case, when D equal to 0. So here D equal to the 0. In that case, this 0 state remains in the next state also. Okay, that is called the hold state. Next is when the previous state is 0 or the present state is 0, what is the next state? This case. Okay, next will be the 1 like this. This happens in which case? When D equal to the 1. What happens further? When the present state is 1 and the next state is 1, 1 to 1. So basically this case. This happens in which case? When D equal to the again 1. And when present state is 1 and the next state is 0, means that this condition exists when D equal to the 0. Fine. So this is the state diagram of our D flip-flops. Fine. So you know how to add asynchronous inputs to our flip-flops. We already discussed 2 asynchronous inputs, that is the reset and the clear states. So if I am saying this is D flip-flop, this is the input and this is the clock, and here we can represent this. So this is preset, and this is clear, and the output is Q, here the Q bar. Okay, both this preset and clears are active low pins. Fine. If we remove this bubble, fine. If we remove this bubble from here, then it becomes like this. Then it becomes active high pin. Fine. Next is our T flip-flop. Fine. So T flip-flop is also called the toggle flip-flops. As the name says, toggle flip-flop means its output toggles. You know, in the JK flip-flops, when both inputs are 1 1, only in that case our output toggles in each clock, means our next output, that is Qn plus 1, is the inverse of the previous output. Fine. So the block diagram of T flip-flop is this. So the T flip-flops is derived from the JK flip-flops. You know, in the JK flip-flops there are three inputs, J, K and the clock. This is basically the clock, and two output, one is Q, second one is the Q bar. And here in the T flip-flops, when I connect this J to the K and this inputs I am denoting T. So now here J is basically equal to the T and K is also equal to the T. Now the truth table of this T flip-flop. In the truth table, the inputs is one input is our clock, second input is our T and output is Qn plus 1. So what happens here, if clock is 0, fine. If clock is 0, then what is the output of JK when clock is 0? So output remains in that previous states, that is called the memory. What happens if clock is 1, T is 0? If T is 0 means both J and K becomes 0, 0. What is the output in that case when both inputs are 0, 0? It remains in hold state. Fine. So Qn plus 1 is equal to the Qn in that case. In the next state, when T equal to the 0, means when both J is 1 and K is 1. What is the output in that case? In that case, output is basically the inverse. Next state is basically the inverse of our previous states. That is the, we are saying, toggle state. So when T is 0, it is Qn. When T is 1, it is Qn bar. So that's why we are saying this is our T flip-flops. So here it is also clear from here that when both the inputs are same, only in that case our JK flip-flops can be renamed as the T flip-flops. Fine. Here both J and K are connected to each other and one input, that we are saying as the T inputs. Now we will derive our characteristics table from the truth table. You know, in the characteristics table, so first input is T, second is Qn previous states, and next is Qn plus 1. So if T is 0 and the previous state is also 0, what will be the next state? Next state is, so here if T is equal to the 0, then from here it is clear. If T equal to the 0, then Qn plus 1 is equal to the Qn, means this. Now if the T is 0 again and Qn is 1, then what is the value of Qn plus 1? It is 1, because see here Qn plus 1 is equal to the Qn when T equal to the 0. When T equal to the 1 and previous state is 0, then it toggle. Now according to the truth tables, now it toggles. Now if the previous state is 0, it converts to the 1, and if the previous state is 1, it converts to the 0. So from the characteristics table, can we derive its characteristic equation? So here it is 1, here it is 1, so we can write Qn plus 1 is equal to the T bar Qn plus T Qn bar. Fine. So this is basically what? This is the XOR of T and the Qn. Fine. So this is its characteristic equation of our T flip-flops. So now we will study the excitation table excitation table of our T flip-flops. You know, in the excitation tables, what are the inputs? Input is Qn and the Qn plus 1, and output is T. So here are 4 combinations. So what are the 4 combinations? This is 0, 0, 0, 1, 1, 0 and the 1, 1. What happens if, see what happens here, the Qn plus 1 is equal to the T XOR Qn. Fine. So if both 0, 0, what is the value of T here? T should be 0 and here 1, 1 and it should be 0. Fine. Because Qn plus 1 is equal to the 1. Fine. Only in that case when both T and Qn is opposite of each other. Fine. So here if Qn is, here Qn is 1, so T should be opposite of this Qn, and here Qn is 1 and T should be opposite of this Qn, and in both cases this 1 should be same of this Qn and this 0 should be same of this Qn. So this is the excitation table of our T flip-flops. Now can we derive its state diagram from these excitation tables? So you know, in the state diagrams there are 2 states, one is 0 state, second one is the 1 state. Fine. So what happens here, if the previous state is 0, next state is 0, so basically this type. Yes, if the previous state is 0, next state is also 0, in which case when T equal to the 0. Fine. If the previous state is 0 and the next state is 1, in which case when T equal to the 1. Fine. So if the previous state is 1, next state is 0, means that this state happens when T equal to the 1. When Qn is 1, previous state is 1, Qn plus 1, next state is 1. So it happens in which case? When T equal to the 0. So this is the state diagram of our T flip-flop. Fine. Now I am taking one example based on this D and T flip-flops. So this is our one sequential circuits. This is D and this is clock. Fine. And this is Q. This is Q bar. And this is connected to one mux which has I1 is this, I0 is this, and this is over A, and this is Y, and this Y is connected to here, and this Q is connected to the I1 and this Q bar is connected to the I0. Fine. So draw the state diagram. Draw the state diagram for this sequential circuit. So state diagrams, here it is clear that this Y is the output and A is the controlling input. Fine. Now it is clear that in the state diagrams there are 2 states, one is 0 and the 1. If I am saying our present state is 0, means the Y is 0 here and now D becomes 0 and this Q becomes 0, because in the D flip-flops we know Qn plus 1 is equal to the D here. So it becomes, Q becomes 0, then QR is 1 here. Fine. If A is 0, what is the first case? If A is 0 here, then what happens here? If A becomes 0, then in the mux, if the select line is 0, then the first input, that is the I0, is propagated to the output and Y becomes I0 here and the I0 is 1. So or now the or state is changing to the 0 to the 1. Fine. So this one, in which case when A is equal to the 0. Now the second case, if A is equal to the 1, if here A equal to the 1, then what happens? This I1 is propagated, means Y remains in the 0. If you consider, if we are saying that present state is 0 and if A is 1, then it remains in the 0. So here it becomes A equal to the 1 here. Fine. So what happens if our present state is 1? Now we are going to this present state, this one. Now if present state is 1 here and A is 0. Fine. So what happens if the present state is 1? Fine. So if I am saying over this present state is 1, if for present state this y is 1 here and it becomes 1 here and this becomes 1 and this becomes the 0. Now if a is equal to the 0, then what happens? This I naught is propagated to the outputs and y becomes the 0 against this state. Now in which case when a equal to the 0, what happens if a equal to the 1? Here if a equal to the 1, then this is propagated to the output and this is 1 here, so it remains in the same state. So a equal to the 1. So this is the state diagrams of this sequential circuit. This type of questions are very important from the gate perspective. Our next topic is race around condition. So race around condition is the disadvantages of level triggered JK flip-flop. So basically this is the disadvantages. In the race around condition, when both j equal to the 1, k equal to the 1, you know when both inputs of our JK flip-flops are 1, then output is in the toggle state. Means if the previously output is Qn, then in the next state it becomes Qn bar, again Qn, again Qn bar, like this. So if the delay of our JK flip-flop is less than over the clock pulse width, in that time the output is unpredictable. And this condition is called the race around condition. How? We will study this race around condition by taking our JK flip-flop example. So what happens? Suppose this is our circuit diagram of our JK flip-flop. This is S, this is R, this is Q, this is Q bar, and here I am putting one AND gate, this AND gate, and this Q bar I am giving to the input of this AND gate, and this is K. Another AND gate, this is K, and the input here, this is. So this is basic, and this is I am saying clock. This is basically our JK flip-flop. So I am saying this is our clock. Fine. So now what happens if j equal to the 1, k equal to the 1, and initially I am saying q equal to the 0 and q bar is 1. Now it becomes 1 1 and it becomes 0 here. So the input of these AND gates are 1 1. Here the output becomes 1. Here the 0. If the input of SR flip-flop is 1 and 0, then its outputs becomes to the 1 set state. So initially I am saying the delay of this SR flip-flop is TPD1. Fine. So here the output is changes from 0 to 1, it changes 1 to 0. So this is our clock. Fine. After TPD1, it becomes again 1. Fine. Now it becomes 1. This 1 is given to here, it becomes now 1. It becomes now 0. And this now 1 changes to 0 and 0 changes to the 1. And the output now changes to the again 0 and again 1. Again after which time TPD1. And this process repeats itself several times in this clock period. And here at this is our Qn state, this is Qn plus 1. So here this output becomes unpredictable. So this condition is called the race around condition. And this race around condition exists only in JK flip-flop, only level triggered JK flip-flop, because or this output changes in this level. Fine. So this condition arises only in the level triggered JK flip-flop when J equal to the 1 and K equal to the 1. Now then how to remove this race around condition? So it is clear. Can you please tell me how to remove this? So if this is our TPW, means the pulse width of our clock, and this is our full clock cycle TCLK. Fine. Now, how to remove this race around condition? If the delay of our flip-flop TPD1 is greater than TPW, fine, means this full pulse width of our clock is lesser than its delay. In that case, this race around condition can be removed, and the other case, this TPD1 should be less than equal to the TCLK. Fine. This is the total clock pulse of total clock period of this clock should be greater than this TPW, means here like this. Fine. So only in that case this race around condition can be removed. Second is the race around condition shall be removed only when we use the negative S triggered or the positive S triggered, means the S triggered flip-flop. Fine. This condition is not exist in S triggered flip-flop. It only exists in the level triggered flip-flop. So third remedy of this race around condition is the master-slave flip-flop. This is alternative of JK flip-flops in which the race around condition is removed, and that is called the master-slave flip-flop. Fine. So now we will study about the master-slave flip-flop. Now the master-slave flip-flop. So basically, in the master-slave flip-flop, as the name suggests, there are two flip-flops in this. So basically, we can say there are two JK flip-flops. One act as a master and second act as a slave. So, for example, this is our master flip-flop. So this is our master flip-flop, master JK flip-flop, and next the slave JK flip-flop is cascaded here. And this QM is cascaded to the over the slave flip-flop. Fine. So this is our slave flip-flop, and this is the final output of our slave JK flip-flop or the full master slave flip-flop. Fine. And this is our clock. Fine. And this clock, please pay attention here. This clock in the master slave flip-flop, both clock is inverted to each other. Fine. Here the directly clock is given, and here so NOT gate is connected here to invert this clock. Now please see here this. In this master slave flip-flop, basically the feedback, this Q bar is given here as the feedback to the master flip-flop like this. Fine. And here this Q is feedback to this master flip-flop like this. Fine. So this is now complete master slave flip-flop. Fine. So what happened here? if j equal to the 1, k equal to the 1, fine, and suppose I am assuming here q equal to the 0 and here q bar equal to the 1. So now what happens here, if q equal to the 1, if q equal to the 0 and q bar is 1, then this 1 is feedback here, fine, and this clock is also 1. Now I am saying this is our clock and this is the clock for the slave flip-flop, fine. So this is our clock for the slave flip-flop. I am saying this is clock 1, this is clock 1, fine. So here's 1, all the three inputs of this NAND gate is 1, 1, 1, and here's the output becomes 0, and here's all this clock is also 1, k is 1, and this is 0, fine, and this becomes 1, and this is our basically what? This is our the latch, fine. So if the inputs of the latch is 0, 1, then what will be the output? Output is basically over 1 and the 0, fine. So please note that here in this only this positive cycles, in this positive cycles only this master's flip-flop becomes on and the slave flip-flops becomes off in this states, because this is negative, this is negative level, fine. So that's why this slave flip-flop is off in this state, fine. So what happens after this clock? What happens after here? After here this clock 1 becomes 1 here, fine. So after that what happens? This 1 is given to here and this clock is also becomes 1, and after that it becomes here, it becomes 0, and it becomes here 0, it becomes 1, and the output is changes from 0 to 1 and 1 to 0. So what happens? Now the total time period of this master slave flip-flop is greater than this cycle now, greater than TPW, and that's why this race around condition can be removed here, fine, and the output is predictable here in the master slave flip-flop. So this is the working of master slave flip-flop and how the race around condition is removed in this master slave flip-flop. And this master slave flip-flops we can design from the D flip-flops, like first this is complete JK flip-flops, and this in the D flip-flop, this can be changed to D flip-flops, and also this can be changed to D flip-flop, because D flip-flop is nothing. D flip-flop is basically there is one data j equal to the k equal to the d, fine. So this is our D flip-flop. So master slave flip-flop can be designed from the D flip-flop. Now the next topic of this lecture is conversion of one flip-flop to the other. So the procedure used to convert one flip-flop to the other is this. So in this procedure, first we have to construct required flip-flop characteristic table. We already studied about the characteristic table of all the flip-flop. So in the first step, we have to construct the required flip-flop characteristic table. Fine. Suppose we want to convert JK to the SR. So first we have to require the characteristic table of our SR flip-flop, and then in the next step we have to fill available flip-flop excitation table. Fine. So from this characteristic table you have to fill the available flip-flop excitation table. Fine. So here suppose I am saying JK to the SR. So here the JK is the available flip-flop. So now you have to fill available, or you have to write the excitation table of the available flip-flop. So third step is you have to write the excitation equation. Fine. Then in the next we will study all these procedures by taking one example. In the next step we have to minimize the logical expression equation. Fine. So by using K-map and other standard methods, you have to minimize that logic equation. Then in the final step, you have to draw the circuit or implement the circuit. Fine. So now I am taking here one example. Now we convert the SR to D flip-flop. Fine. So in the first step is construct required flip-flop characteristics table. So which is required flip-flop here? Here the D flip-flop is the required flip-flop and SR flip-flop is the available flip-flop. Fine. So for in the first step you have to construct the required flip-flop characteristic table. So what is the characteristic table? You know, we already studied about the characteristic table of D flip-flop, here D, Qn and the Qn plus 1. So there are four combinations 0, 0, 0, 1, 1, 0, 1, 1. So what is the output here? Here the output is 0, 0, 1, 1. Fine. So because in the D flip-flop Qn plus 1 equal to the D, that's why here this Qn plus 1 is equal to the D here. Fine. So now in the second step we have to fill available flip-flop excitation table. You know, here the available flip-flop is the SR flip-flop. So you know that in the excitation table of our SR flip-flop, the inputs is Qn and the Qn plus 1. Fine. So here we write S and R. Now fill the excitation table for it. You know the excitation table for SR flip-flop. In the next case 0, 1, 1, 0 and this is this. In the third step, you have to write the excitation equation. Fine. So what is the excitation equation for this S? So here's this S equal to the sigma M2 because see this is 1 here. Fine. So sigma M2 and plus 1 don't care condition. Don't care condition is at 3. Fine. So how to minimize this equation? So we can use the K-map here. So this S should be, what are the inputs here? This should be in terms of here D and the Qn. Fine. So here we write the D and here we write the Qn. Fine. So 0, 1, 2 and 3. Fine. So there is one pair of this, then this is D. And now the S is equal to the what? D here. Fine. Similarly, what is the equation for the R? R is equal to the sigma M1, this one only, and 1 is here don't care, this is don't care condition, and then similarly by using K-map we can solve this thing through the K-map. So here R becomes D bar. Fine. So here we got the value of S here, we got the value of R here. Now what is the next step? That is fifth step, draw the circuit or implement the circuit. You know, we have to design the SR to D flip-flop. So here this is available flip-flop, this is S, this is R and this is clock, and this is our Q and this is Q bar. Now you know the S is equal to the D and or R is equal to the D bar. Fine. So this is our SR to D flip-flop. Fine. So by using this procedure, we can design all other flip-flops to other flip-flop. Fine. Similarly, if we want to design JK to D flip-flops, then I am writing directly the final equation. So here J equal to the D and K equal to the D bar. Now suppose we want to design JK to T flip-flops, then here J equal to the K equal to the T. We already studied about this. Now we want to convert JK to SR flip-flop. So here's the J equal to the S and R equal to the or K equal to the R. Fine. Suppose we want to convert SR to JK flip-flops, inverse of this. Then here the S is becomes the J Q bar and R becomes the K Q. So like this we can convert all other flip-flops to the other flip-flops. So now this is the end of this lecture. So if you have any query, then you can send me mail. Thank you for your attention. So for more video update, please subscribe this channel. Fine, so that every information regarding your course or regarding this digital electronics lectures you can get easily. Fine. Thank you for your attention.